Hello again. So now that we have some of the basic concepts down, we've seen some examples of how to apply the chain rule. Let's look at a few more complicated exercises and applications. So here we are asked to differentiate a couple functions. The first one, the function is the square root of the quantity x over x minus 1. So if we think of this, remembering that the square root is the same as raising something to the 1/2 power, this is the same as writing x over x minus 1 to the 1/2 power. So then calculating the derivative of this, I'm going to think of the x over x minus 1, that's being raised to the 1/2 power. So then the derivative, f prime of x, I'd have 1/2 of the quantity to the negative 1/2 power, and then I'd have to multiply that by the derivative with respect to x of that same quantity. X over x minus 1, x over x minus 1. Now, the chain here, the differentiating with respect to x, x over x minus 1. So within that chain, I have to apply a quotient rule. All right, so this is where things get more complicated. I'm having to use multiple rules here to calculate this derivative. All right, so I'm just going to leave this first factor alone, 1/2 by x over x minus 1 to the negative 1/2 power. All right, now let's apply the quotient rule. The derivative of the top is 1, leave the bottom alone, minus, leave the top alone, derivative of the bottom is 1, and then over the bottom, square. All right, so then, again, I'm going to leave this first factor alone, 1/2, by x over x minus 1 to the negative 1/2 power. And then cleaning up this expression, let's see, 1 times x minus 1 is x minus 1 minus x. So that would be a negative 1 over x minus 1 square. All right, so what I would do then is bring that negative out front. So I would write f prime of x is maybe negative 1/2 by x over x minus 1 to the negative 1/2 times 1 over x minus 1 square. And we can there are ways we could simplify this by taking into account the x over x minus 1 to the negative 1/2 and rewriting that with a positive exponent and rewriting that with the 1/2 power and simplifying it. But is it really necessary? I don't know. So I'll just leave this one alone. All right, why don't you try this one out? Take r of t equals e to the t sine t and calculate its derivative. All right, so how I see this is I have r of t is e to a power. The derivative of the exponential function is the exponential function. All right, so r prime of t is then going to be e to that power times the derivative with respect to t of that power. So e to the t sine t by the derivative with respect to t of t sine t. All right, so calculating that derivative, the derivative with respect to t of t sine t, that is a product. That's the product of t times sine t. So I'm going to have to use a product rule there. So then r prime of t is e to the t sine t, and then applying the product rule, I'd have 1 times sine t plus t times cosine t. So then r prime of t is e to the t sine t times sine t plus t cosine t. All right, so we have to be aware of situations where we have to apply multiple rules, either the chain in combination with a product or a quotient, or the chain in combination with a power. And of course, we're going to be learning some other rules. We're not done learning rules. There's a few others we still need to know. So things we need to be aware of. All right, so let's look at a couple applications. Let's see, determine any intervals where h of w is w squared minus 1 e to the 2 minus w squared is increasing. All right, so where is it increasing? Well, we've seen problems like this before. We know if it's increasing, that means we want h prime of w to be positive. All right, so we've got to calculate the derivative function and find where it's positive. Well, again, we're going to first calculate the derivative function, find where it's equal to 0, and then compare. We've done this before. We're just introducing it with a new type of function, and we're going to probably have to apply the chain rule. All right, so let's analyze this function. We have h of w is w squared minus 1 by e to the 2 minus w squared. So if I look at this, I see I have a product of functions, and I see an e to a power. I'm going to have to use the a chain rule there because that's a composite. All right, so let's see. h prime of w, differentiating the first factor, 2w. Leave the second factor alone, e to the 2 minus w squared, plus, leave the first factor alone, w squared minus 1. Differentiate the second factor. All right, so differentiating e to the 2 minus w squared, that's e to a power. So that would be e to the power times the derivative with respect to w of that power. Right, so in calculating the derivative of e to the 2 minus w squared, here I'm having to use a chain rule. Right, so here's the chain. So I had to use the product rule to calculate the derivative of the function, but then within that, I had to use a chain rule. All right, so let's see, that's 2w e to the 2 minus w squared plus w squared minus 1 e to the 2 minus w squared. Then the derivative with respect to w of 2 minus w squared would be negative 2w. All right, so notice something that, if we're sort of thinking ahead and remembering that I'm going to want to find where this is equal to 0, so then I can find where it's positive. Notice that I have a common factor of e to the 2 minus w squared. So let's factor that out. E to the 2 minus w squared, and that's being multiplied by, in the first factor, 2w, first term, 2w, and in the second term I have w squared minus 1 by negative 2w. So that's e to the 2 minus w squared times 2w minus 2w cubed plus 2w. So that's e to the 2 minus w squared. And hey, notice that I can factor out a 2w, and then well, actually, you know what? I'm going to take this back a step. Let's simplify first. That's negative 2w cubed plus 4w. Now let's factor out the 2w. Or actually, I could factor out a negative 2w. All right, so I have an e to the 2 minus w squared. I have a negative 2w, and then I have a w squared minus 2. So here's a way that I can write h prime of w. So there's the derivative. Now we want to find where it's equal to 0. Well, first we find where it's we want to find where it's greater than 0. First we find where it's equal to 0. All right, so let's solve where is h prime of w equal to 0. So that would then, since it's already in a factored form, we would have e to the 2 minus w squared equals 0. That can't happen. Exponential functions can never equal 0. We have negative 2w equals 0, which means that w equals 0. And we have that w squared minus 2 equals 0, and that implies that w is the positive or negative square root of 2. So we have three important values here, 0 and plus or minus root 2. Let's think of our number line. Here's negative root 2. Here's 0. Here's root 2. And we test a value in each interval. Root 2 is approximately 1.4. So how about let's test a negative 3 maybe. Let's test a negative 1. Let's test a 1. And let's test a positive 3. And we're testing this into h prime of w. And I'm going to test into the form e to the 2 minus w squared times negative 2w times w squared minus 2. All right, so testing negative 3. E to a power, remember, e to a power is positive. So e to the power is positive. Negative 2 times negative 3 would be positive. Negative 3 squared minus 2, that would be 9 minus 2, which is positive. This interval ends up being a positive. Testing negative 1. E to a power is positive. Negative 2 times negative 1 is positive. Negative 1 squared minus 2, that would be 1 minus 2, which is negative. Positive times negative is negative. Testing 1. That would end up being positive. Negative 2 times 1 is negative. 1 squared minus 2 is negative. Positive times a negative is positive. And finally, testing 3. That would be a positive times a negative times a positive, which is negative. All right, and we wanted where it was increasing. It's increasing where the derivative is positive. So 2 intervals. So I would say that h of w is increasing on a negative infinity to negative root 2, and again on 0 to root 2. All right, here's another example. Determine any intervals on 0 to 4 pi where y of t is cosine squared t minus 2 sine t is decreasing. Now would be a great time to pause. Try this one out on your own. All right, I hope you paused and tried it. Again, the best way to learn how to do this is to try it out on your own. And if you make a mistake, to figure out where you made the mistakes. You won't learn as much just by watching me do it. All right, so again, let's see, we want to find where y of t is decreasing. So similar to the previous exercise, I'm going to calculate a derivative, and I'm going to find where it's equal to 0, and then I'll compare each interval. All right, so let's see, y of t is cosine squared t minus 2 sine t. That's the same as writing cosine of t square minus 2 sine t. So I'm going to have to use a chain rule here for the first term. Y prime of t is 2 times cosine t to the first, and then the derivative of the cosine t is negative sine t. And then let's see, minus 2, the derivative of sine t is cosine t. All right, notice that I can factor a 2, I can factor a cosine t. So that's 2 cosine t. Actually, I can factor out a negative as well. Let's factor out the negative. let's factor negative 2 cosine t times sine t plus 1. All right, and let's set that equal to 0. All right, so y prime of t is equal to negative 2 cosine t by sine t plus 1. So let's solve y prime of t is equal to 0. It's already in a factored form. So negative 2 cosine t could equal 0, which implies then that cosine t is 0. And over the interval 0 to 4 pi, where is the cosine 0? The cosine is 0 at the odd pi over 2s, if I remember right from trigonometry. So let's see then. Cosine t is equal to 0 would imply then that t is pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And then that's where we'll stop since we're only going up to 4 pi. All right, the other factor, sine t plus 1 is 0. That implies that sine t is negative 1. And where is sine t negative 1? So if we're thinking of the unit circle, that's the bottom of the circle. And so then that's 3 pi over 2 and 7 pi over 2 over the interval. So we see that some of the roots here are repeated, and that happens sometimes. All right, so I see that there are 4 important numbers on the number line that we are considering. All right, so here's my number line, and it stops at 0, and then I have pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and then it stops at 2 pi. I didn't draw this very well, but I hope you understand the general picture. All right, and I'm going to test into, all right, so we're going to test each interval. I'm going to test into negative 2 cosine t by sine t plus 1. All right, so I'm going to test, how about pi over 4, 3 pi over 4, actually, I don't have to test, let's see, pi over 4 is certainly good. Between pi over 2 and 3 pi over 2 is pi. Between 3 pi over 2 and 5 pi over 2 is 2 pi. 3 pi. Oh, and this should be 4 pi on the end, not 2 pi. Yeah, something didn't make sense there. And then finally, let's see, how about between 7 pi over 2 and 4 pi, that would be about 15 pi over 4. This isn't actually that difficult. I know it might look like it's difficult, but it's not too bad, because let's look at this. We have negative 2 times the cosine of t times sine t plus 1. If you remember back from trigonometry, the graph of sine t plus 1 would be the graph of the sine function shifted up 1 unit. So if we shift the sine function up 1 unit, it looks roughly like this, where it hits 0 but never goes below 0. And so what that means is the that the function sine t plus 1 is never negative. Sine t plus 1, right? This is sine t plus 1. This is never negative. We found where it's equal to 0 at 3 pi over 2 and 7 pi over 2, but otherwise it's positive. The negative 2 is always negative, and so really all we care about is cosine t. Okay, so again, this is a little bit, if we do a little bit of thinking, it makes this problem a bit easier. So all we have to do is think about the sign of cosine t in each of these intervals. All right, between 0 and pi over 2, the cosine is positive. So I would have, all right, so at pi over 4, all right, so testing pi over 4, I would have the negative from the negative 2. The cosine between 0 and pi over 2, the cosine is positive, and then sine t plus 1 would be positive. And so this ends up being a negative. Using a similar idea, between 3 pi over 2, between pi over 2 and 3 pi over 2, the cosine is negative. So I'd have a negative times a positive, that would be positive. Between 3 pi over 2 and 5 pi over 2, the cosine is negative. Negative times negative. Between 3 pi over 2 and 5 pi over 2, the cosine is positive. So I have a negative times a positive, that would be negative. And we can continue this analysis. The interval between 5 pi over 2 and 5 pi over 2 and 7 pi over 2 is positive. And between 7 pi over 2 and 4 pi over 2 is negative. So then where is it decreasing? All right, so then y is decreasing on 0 to pi over 2, on 3 pi over 2 to 5 pi over 2, and on 7 pi over 2 to 4 pi. Alright, so that concludes this video with some more examples of the use of the chain rule and some applications. Alright, now we're going to be using the chain rule from now on in calculus, so you really need to spend some time and practice with it. It is probably the area in the rules for derivatives, it's the area that students have the most difficulty with. Alright, so I will see you in the next topic. Have a great day.